Joined the robotics club there, went to a lot of competitions. After that, I joined the lab in the electrical engineering department, got my master's there. So that's kind of like where I transitioned to like focusing on being an actual roboticist.
For someone looking to begin their career as a specifically robotics software engineer, there is one confusion that happens is should I first get a physical robot or is there any possibility that I can get good enough to get into a company through simulations? To what extent should they rely on simulation and what are the aspects they can learn from simulations?
I know that one of your previous people that you interviewed said you need to get out of simulation. And I understand where he's coming from when he says that. But also, some people need to get into simulation. And the reason I say that, I'll circle back around to like, I'm just new in robotics part of this.
If a person wants to get into industry, there are things like communities and engaging with people to get to the point of an interview. That's one scenario. Once we are inside of the interview, the technical aspect, what do you think as a robotic software engineer, a junior role, an ideal developer should have, the thinking, the approach, the projects? What do you suggest for a junior robotics engineer? Writing the software. Once that is done, the basic process is done. We need to engineer it. There comes the part of testing and engineering the already available stacks, writing plugins. How do you look at these things? Starting a robotics company, you might have experienced with the startups. What should be the approaches towards solving a real world problem with the robot and how some bad experiences would be appreciated as well?
So, first off, I would say that if you like building robots, starting your own company is a horrible idea. As the CEO of a company, you spend your entire day trying to promote the product, trying to sell the product, trying to talk to businesses, and this is a vital role. You're going to lose all of your like engineering opportunities there. So I would say the first thing you should do from a common pitfall, which I personally don't know how to do, right? But the pitfall is roboticists tend to find a robot and then look for a problem. A robot is a technology, never actually a product. Okay. It's a technology that you can use to make a product. And really, when you're starting a company, doesn't matter what it is, you should find a problem first to be solved by somebody. You should provide value there for somebody.
Today, we have a very special guest with us. He's a senior robotics engineer currently serving at Picnic, and we are here to understand a lot of technical stuff in robotics for software architecture and good practices. So, Griswold, how are you?
Hi, Luke, man. Nice to see you.
So, we have been having sort of a discussion earlier as well. There are a lot of things to unpack, and we will be doing that. You have been in this professional robotics development for almost a decade, and there is a lot of learnings, a lot of experiences that you might have gained. So, how did this started? What was your journey of the start into robotics?
So I'm from New Hampshire, which is a state in the U.S. that we're very proud of a lot of things in New Hampshire, but it's not like some place where you get a lot of exposure to electrical engineering, software engineering. At least when I was growing up. Now, of course, New Hampshire is like really famous for FIRST robotics, and you go to those big student competitions. But when I was in high school, there wasn't a lot of robotics, so I feel like that I was exposed and like first like inspired by robotics when I was about 8 years old. I don't know how many people in this audience know Rodney Brooks, but he was a professor at MIT. He now, had the company Rethink Robotics, and he has another company on the West Coast. But he used to work on this robot at MIT called Cog, which was this humanoid. And, I always used to think like seeing the arms move around was kind of cool because every kid loves, robots and dinosaurs when they're growing up. But then I watched a special on Cog, and he was programming the robot to think. He was trying to make brains, and that just kind of like amazed me. So I would say that was like the spark point. But frankly, I never thought that I was smart enough to do anything in robotics. So I didn't really go directly there. I graduated high school, and I didn't really know what to do. So I ended up going into the Navy. I went into the Navy for 6 years because they would train me on electronics, and that's something I thought I would be really interested in, which I was. I still love electronics, but that's kind of like this divergence that I took, right, from robotics. And the nice thing about the Navy is that I was able to get some good benefits from that. So once I left the Navy, once I finished serving, I went to community college for network engineering. I was going to try to do network security, which I did for a couple years. But once I had finished community college, I was going to move to New York City because I have family there. And as I was moving there, my father suggested that I apply to university for robotics, and because I had some GI Bill money left over to use. And he told me the worst thing that I could do was fail. He said, go try. And if it doesn't work out, you already have all these other things in your career and it'll be fine. And it turns out I didn't fail. I found a really good community at NYU Polytechnic University and joined the robotics club there. Went to a lot of competitions, had some really good classes with my professors. And then after that, I joined the lab in the electrical engineering department, got my master's there. So that's kind of like where I transitioned to like focusing on being an actual roboticist.
Interesting. We'll come to the competitions and this robotics communities later. I want to
Yeah.
get started into things that people are most interested in, as you have spent a lot of time in the professional development and code that is in the products in real robots. So for someone looking to begin their career as a specifically robotics software engineer, there is one confusion that happens is, should I first get a physical robot, or is there any possibility that I can get good enough to get into a company through simulations? To what extent should they rely on simulation, and what are the aspects they can learn from simulations?
Yes. So I feel like you can learn a lot from simulation. I know that one of your previous people that you interviewed said you need to get out of simulation. And I understand where he's coming from when he says that. But also, some people need to get into simulation. And the reason I say that, I'll circle back around to like, I'm just new in a robotics part of this. But the reason I say that is there's a habit of roboticists to feel like that they can only test their code on the robot, right? And when you've got like a, 1 pound Arduino robot, I still don't think that's really a good way to do it, but at least it sounds more feasible. But I've been on projects where the robot was multiple tons, right? And the only way to validate a lot of the code was to run this multiple ton 4-arm wheeled tractor, right, through a field. So I feel like that there is, from the professional side, right, you need to invest in both of those things. And I think we're going to talk about that later. As somebody who's just coming into robotics, I feel like that you need to do a little of both. So I'll give you an example. I had a colleague while I was at Nita Robotics, and he was excellent at what he did, right? But he was a junior engineer, and he'd done a lot of software, right? And he'd done simulation work. But what was harder for him is to see kind of like the forest for the trees. And so I would advise that every roboticist should at least put together, some sort of Arduino based robot at a minimum, right? Physically go through as much of the pipeline as you can, because I don't really think there's an end there, right? You start working on a little hobby robot, right? And then you will get to one thing and then you will do the next thing. And suddenly you need it to like GPS navigate and obstacle avoid, right? And so like you can scale how much your little toy robot is, and you go through a lot of challenges. Like you realize that your sensors aren't good enough, your encoders aren't good enough, your wheels aren't strong enough, your traction isn't there, your field of view isn't there. You can't localize because you chose the wrong sensors, right? So you learn a whole bunch of those things by going through the pain. But on the other side of that, right, if you're a person focused on just hardware integration, you also get a little bit too much in the weeds, right? You get focused on like, how many ticks for my encoder count are, right? And maybe you forget, because robots are very deep, right? You forget that, I need to do the correct sampling, uniform sampling density for my particle filter, right? Or more likely, if you're going to like walk into a robotics company, it's not necessarily that you've got to be the guy who writes the particle filter from scratch. I'm using particle filter as just one example. Obviously, there's any number of algorithms that you could name. It's more likely that you need to be the guy who's tuned a particle filter before, right? Understands enough concepts of getting a particle filter to work in simulation or on the robot, right? So I feel like that if you are good enough at Gazebo or Majoku or VREP or any other simulation framework to have gotten a robot to run around, I mean, the AI gyms, right? They use Majoku, but you've also done some hardware integration even at the hobbyist level, but more than just I put together an RC robot, right? That's kind of like maybe one of the differentiators there I should mention. So like anybody can go to Walmart or some store and buy an RC robot or buy an RC kit. And that's definitely part of it, right? For example, my robot right here is called Banshee. And when we were at Fetch, we used to do a 3-pound plastic fighting league, right? And so that robot is an RC robot, but if you just left it there, maybe that doesn't give you quite as enough experience. Like for example, this robot doesn't need encoders, it doesn't need obstacle avoidance because the human is all of those things. So if you take it like another step further, and this is where I think the role of participating in competitions can really help.
Okay. A lot of learnings can be done through simulations, but if we have a hardware, it gives us an edge.
A lot of
Yes.
learnings should be done through simulation. And
Okay.
roboticists need to know how to do both. And obviously, we'll talk about it later, right? About like the role of simulation in the robotics pipeline. But, you need to be good at simulation and knowing the appropriate level of simulation, I guess I should say. So, for example, kinematics, right? So the study of the geometric positioning of the robot in space, right, as opposed to dynamics, which talks about torques and forces. There is a lot that can be done in simulation that has no physics, where you're just positioning the robot in space, doing those mathematical calculations, but you're referencing something external to the robot, right? So like, did the robot arm get to a certain position? And is that position near the grasp target, the cup that I'm trying to pick up? Or my mobile base was trying to path plan, and it path planned towards these obstacles. Did it stay far enough away from those obstacles? All those are simulations in the sense that you're validating your algorithm with an external environment, but you didn't have to invoke physics. And actually, in our experience at Picnic Robotics, we've written quite a number of test suites where that's the case, where you just needed to worry about the positioning of things before you had to start thinking about the dynamics. So a roboticist should be familiar with a wide range of those things. One thing I always tell people about having a robot startup, which we can talk about later too, there are startups where they just do wireless, right? Where they just do wireless communication. There are startups where they just focus on mapping. There are startups where they just focus on making a thing that drives around well, right? I could keep going. A robotics startup ends up being a company that is trying to do like 4 or 5 startups all at the same time, right? And so it tends to be roboticists are similarly a really cliche way of saying it, because they say it in software engineering all the time. The roboticists have to be very T-shaped. I don't know if you ever heard this expression where like you've got to have a lot of breadth on a lot of subjects and have basic competencies there, but usually you should be an expert in one thing.
Definitely. There are a lot of things involved as well. And if we are only talking about software, even, it becomes a T shape as well. Hardware and those are other things. Coming to the point, I want to progress in the form of first talking about a person who wants to get into the industry, then starting a company, and then we will discuss a lot of things in building a product. If a person wants to get into industry, there are things like communities and engaging with people to get to the point of interview. That's one scenario. Once we are inside of the interview, the technical aspect. What do you think as a robotic software engineer, a junior role, an ideal developer should have, the thinking, the approach, the projects? What do you suggest for a junior robotics engineer?
So you have to have a competency in at least two programming languages. And when I say a competency, so in my field, right, I'm very used to there being C++ and Python as the basic competencies, right? In other companies, there might be more of a shift towards Rust, right? Python still seems to come up in a lot of places because, besides machine learning, there's a lot of things, if you're in the ROS community, right, where it's just easier to just get those basic things running. But when I say like a basic competency, it's hard to discuss things like leet code or hacker rank because using those problems to learn software engineering usually breeds bad habits because they tend to direct you towards performance at all costs, even if it's not maintainable code, which there's an expression that software engineering is programming over time, right? So you never write the code once, and the code is almost always wrong in like a week, right? And there's another expression that code rots, and that tends to be because the environment around it is actually changing. So like you can write the most correct code right now and it could be perfect. For example, the code for Banshee there, I wrote that, 8 years ago and it's performed perfectly every time. But the requirements for Banshee have never changed. The hardware for Banshee has never changed, right? And it tends to be software is thought of as soft because it's changeable. And so, especially in a startup, right, the software is changing constantly. And so, whatever was appropriate one day may not be appropriate the next day. So, if you're a junior engineer and somebody has to just get you past some of the basic competencies for this dynamic changing environment, there's going to be a struggle there, right? People don't want to have to teach you the basics. So in my field, right, you should be familiar with a bunch of the standard library algorithms, the C++ standard library algorithms, right? You should be able to program a very small multi-threaded application easily. You should be familiar with, okay, so this is one of those like weird things I guess I'll point out. If you were trying to apply to some place like Microsoft or Amazon, some sort of FANG company, right? Some sort of cloud-based company, their suite of algorithms, even their basic algorithms, differ quite a lot from what's in robotics. So I got asked a question one time in an interview where somebody wanted to know how to program something called a tree, TRIE, right? Basically what it is this hierarchical index database, right? So like the database keys themselves branch off so that you can more efficiently get to a set of words, right? Because they're talking about storing millions and millions and millions of, probably even more, that millions doesn't cut it, of all these records, and they need them very quickly. This is an algorithm that I've never heard of anyone in robotics use at all. I hadn't even heard of the words for that algorithm, right? But a lot of those people will never heard of a particle filter or a Kalman filter, right? Which are things that, roboticists at least have to know what they are. They have to know what these state estimators are. So there's two parts to it, right? I expect a junior engineer to at least be familiar with a suite of algorithms, like with classes of robotics algorithms, at least know their names and what they're for. I expect them to be able to program one of them okay, like not efficiently. Efficiency is a thing that you can work on over time, right? And it's one of those things in software engineering, right? You need the whole context to talk about what's efficient, right? You need to know what computer you're on. I mean, obviously, if you're doing like a triple loop, right? Fine, that's not efficient. People then go too far the other way, right? And they start individually flipping bits. So what I mean by like you need to have a basic competency in a lot of things, a little bit of depth in one of those algorithms. But as far as C++ goes or Python, right? You need to be able to write functions quickly. You need to be able to write classes quickly, know about inheritance hierarchies. You need to be able to use the modern tools in C++ for like, memory safety, right? You need to be able to decompose the problem and talk to me as the interviewer about what you're doing, even if you don't know how to solve it yet. So you need to be able to decompose and think through the problem and show me that you can do it, because that's going to be your day to day, right? So to me, that only comes with having done it a lot, having written lots of software badly and thrown it away. There's another great expression I love. It's called software should be treated like cattle, not pets. So you
Okay.
you raise your software, right? You care for it, but at the moment you need, you should be able to throw it away and start over, right? Um, you wouldn't do that to your
Okay.
pet, right? But your cattle you might harvest or something like that. Um, and this is especially like contentious when you're in a production environment, because in a production environment you can't throw away the world. But on a small scale, you need to be prepared to do that. But when you're learning, you can throw away everything. It's great, right? You can write yourself into these deep holes that are terrible and like get all these negative experiences and then throw it all away again, right? I have a really good friend of mine, Brian Carroll. While we were in the lab together, he rewrote his entire software stack for our quadruped robot about 4 times. He wrote some really horrific code that he showed me, and he's one of the best software engineers I know. So I kind of expect a junior engineer to have written a lot of bad code, but it helps them learn how to write code. It won't be new to them. Yeah. So
Definitely.
I don't know. It's maybe a little bit hard to say. It's not a clear answer, right? But
Yeah.
there's a suite of basic competencies that you should be able to do.
Definitely. And the thing that you mentioned is obviously very important. If someone can come to an interview and tell you all about his or her code, in which they only explain about the problems and the inefficiencies in their code, that's also a good sort of reply.
Yeah.
So, coming to the next step, once a person gets into the company, he spends a lot of time there, build good software practices, and after a certain time period, they think about starting a company, a group of people, and they think about specifically a robotics company. Now, coming to starting a robotics company, you might have experienced with the startups and producing software solutions or hardware solutions for the companies are providing hardware solutions for a certain problem. What should be the approaches towards solving a real world problem with the robot, and how some bad experiences would be appreciated as well?
So first off, I would say that if you like building robots, starting your own company is a horrible idea.
Okay.
Um, I think my former CEO, now Chief Product Officer Dave Coleman, could give some recent experience where, uh, as the CEO of a company, you spend your entire day trying to promote the product, trying to sell the product, trying to talk to businesses, and this is a vital role. Um, you need somebody to do that, right? You need somebody to be out there, right? And like you have to be solving some sort of problem and selling it to someone. Otherwise, you don't have a company, you have a hobby, right? Um, so you're going to lose all of your like engineering opportunities there. So I would say the first thing you should do if you want to start a robotics company is find somebody who wants to be that guy that you trust. I have another friend who's just starting a startup, and he gets to be the technical guy. Now, the CTO of a company has a lot of stress as well, right? CEO, all the C-level people, especially in a small company like less than 20 people, frequently you're going to start with like 4 people, right? Everybody's doing everything, right? And so it's not like you can have your role so cut and dry and like, oh, you only do this and you only do that. You're going to have focuses, but you know, you don't get to be siloed. But at least if you were maybe CTO, maybe lead mechanical engineer, lead software engineer, maybe you get to focus on those more. I want to point out that being a CEO is a very specific job for a type of person who wants to be a CEO. And you should know that, right? Now, starting a small business, right? Maybe like a little 3D printing business, a little hobby robotics business, maybe you can slip away from that. But when most people talk about doing a startup, they talk about taking investment. And so before you ever get close to taking investment, even if it's like, your own money, really, right? Because essentially you're going to say, I'm going to stop having an income and I need to pay rent. I need to eat food. I need to support my family. I need to pay the bills for some period of time until somebody else is going to do those things for me, right? Either that's a angel investor, Series A. Heaven forbid, you can actually sell your product and become profitable, which is a huge challenge for roboticists. So before you ever get to that point, you need to steer away from a common pitfall, which I personally don't know how to do, right? But the pitfall is roboticists tend to find a robot and then look for a problem. And really, when you're starting a company, doesn't matter what it is, you should find a problem first to be solved by somebody. You should provide value there for somebody. An excellent book that I'm sure lots of people have read is called The Lean Startup, right? And what I really liked about that book was they talked about the concept of minimum viable product in a way I had never really heard of before. So when you're an engineer at a company, people will talk about prototype in one is the same thing as minimum viable product, right? And they'll kind of use it as a shorthand to mean just get me one more feature, right? They don't really use the term as it was originally conceived. Whether or not you should do that anymore is one thing, but I think there was a lot of value there. So a prototype, right, is a technology demonstration. Okay. A robot is a technology. A robot is not a product. A robot is never actually a product. Okay. It's a technology that you can use to make a product, right? A more complete example there, right? Let's say you have a robot that's going to take a picture for you in a store, okay? First of all, why do you want a picture taken, right? In my experience, it was, I want to know if there's a product on the shelf. Okay, so what you really want, what the business owner wants, is they want to know if a product is stocked. Now, as a company, I might say, I'm going to use a robot to drive over to where the product is and take a picture, and then use maybe cloud services to do machine learning to determine if something's on the shelf. Maybe I'm using a different sensor modality to directly detect the presence or absence of something, and then I have to report those things in an interface that the customer is easy to use, right? So like the robot, even in that scenario, was just one part of it, right? And there was actually multiple other technologies you had to use to get to that, and that starts to become looking like a product. But if you swap out the robot for a human being, right, you could have the same thing happen. Okay, so in the Lean Startup book, to come back from prototypes or technology demonstrations, minimum viable product is doing the least amount of things to try to deliver value for someone else. A really, really amazing example in that book I thought was there was this person, and maybe they had one other person at the time when they started, and they wanted to make it easier for people to eat healthy recipes, to make healthy recipes at home, but save a little bit of money, right? And so the idea was that if you knew all the deals at your local supermarket, right, whatever supermarkets are local to you, you could match up the best prices at the time with a set of healthy recipes that fit into your lifestyle. Okay. And instead of starting with, okay, what database selection, what Google thing do I need to like get all this information? They started with the CEO would go to the customer's house, sit down with them at their kitchen table, spread out all the coupon books, right, from the local stores, and match up recipes on paper index cards and give them to them, right? And this wasn't an accident. They knew that they were doing it this way on purpose. So they would match all these things up, and only once it started to become difficult for that person to drive to everybody's house and do that with them, did they start investing on an email, chain, right? Only after that did they start investing in like taking payments other than cash, right? Only then did they start to build technologies that solve problem for essentially an already existing product, right? So to flip this example a little bit back towards the robotics world. A company I really like talking about as a good example of this is Bear Robotics. They have lots of competitors. Pudu is another competitor, but maybe if you've gone to a sushi restaurant or some other Asian restaurant, you might notice a lot of waiter robots moving around now. I feel like every sushi
Hmm.
restaurant I go to has a waiter robot. And while that may not be globally true, I attribute it to Bear Robotics because I feel like they were at least one of the first movers in that industry. And the way that company started is there wasn't somebody who had a mobile base and was like, what kind of problem can I solve with the mobile base? There were some ex-Googlers who started a pizza restaurant because they really wanted to cook pizza. And they started running their business and they found challenges in running their business with just two people and hiring employees. And they're like, man, we can make all these pizzas, but just getting them out there to the customer takes all this time. We could build a robot to do that. And so they started with having a problem to be solved. And it just so happened because of their background, they knew that a robot was a feasible thing there, right? Later, with my friend who worked at Bear Robotics, we went to a small business owner during the pandemic, or right after people were starting to open up, and they ran a small brew pub, and it was just a mom and pop store. It was the mom, the dad, and the son. The mom ran the kitchen, the dad ran the bar, and the son, you know, ran tables, right? And they had a fleet of four of these robots, and they said their whole business would have collapsed if they hadn't had these robots to help them with their work. So you have to try to find a problem first to be solved. Recently, I don't know if anyone here is into 3D printing, but there's this YouTube channel called Slant 3D. And Slant 3D recently put out a video where they talked about classifications of problems for people to solve for products, right? And just to bring it up as like problems can be abstract, they brought up fashion being a problem, right, to be solved, right? And the thing there is communicating status to other people. That's one of the things that is solved with fashion. So just to say that products can take on many shapes and forms, you need to find a problem to be solved first, not a robot to solve it. So that's like the first
Interesting.
huge piece of advice I would give to anyone who wants to start a company.
So let's bring up a example to clarify this concept, because this is very important to understand, as all technical people love technology and they want to utilize that into the form of business, but most robotics companies even get closed, and very good companies of robotics get closed for many reasons. But main reason is this, that their robot is ready but the solution is not that attractive to the market. Coming to the point of a solution that is globally required, sort of warehouse automation. Actually, I want you to spend some time on the software architecture part of this specific situation, so we can understand what goes inside of software building, creation, testing, all of these stages. There is a mobile robot with a 2D LiDAR, simple scenario, in a warehouse robot, and it has to go from different locations and different points and different, we can call different pallets and a lot of things. It has some monocular vision, but SLAM and everything is based on 2D LiDAR. So what would be your approach on planning the software, understanding the problem, and creating the software? I want every single detail, as long as you can, so we can understand how actual code is written.
All right, so let's back up for a second then. So we've got a problem, right? And the problem is that the warehouse needs objects delivered, or the warehouse needs an inventory taken. For example, Dextery Robotics, right? They are really making strides in the warehouse, identification, so on. They have this enormous robot that's the size of a tiny. When we were at ROSCON this year, people thought it was actually a part of a building. It was so tall because it can telescope really high, right? Whereas like other companies, like when I was at Fetch, we were more focused on like getting the robot somewhere so people could help deliver. Assuming that we've like identified some sort of like problem there, right? And we're not talking about manipulation. You started off by saying 2D LiDAR. That's not the right way to start. I agree that I probably would use a 2D LiDAR, but let's take a step back and talk about why you might use a 2D LiDAR. Because a lot of things have changed since when I started, working in the industry. When I was getting started at Fetch Robotics, for example, 2D LiDARs were really just the only thing, right? There were depth cameras to be sure, right? The Fetch had, you know, an Asus action camera on it, and the Microsoft Kinect, right, was really popular for people to mount on the PR2, and the PR2 had all these other bespoke cameras on it for research and so on. But a lot of companies were just doing the 2D LiDAR because it had a high reliability and it could fit a number of scenarios. But what are the scenarios to be fit, right? Um, as I'm now working for Picnic Robotics, and Picnic maintains Move It, and they're an ARM company, one of the things I frequently have to explain to ARM people is that mobile bases like this guy, uh, they never know where they are, right? So like an ARM usually has these very high resolution encoders on them, right? And so they can know their state in the world very accurately. Um, Mobile bases are always wrong. They're not fixed to anything. They usually have no absolute reference. If you can have a problem, right, where uh, you know, I'm building a robot for my house, my personal house, okay, and I can put up a big stick that the robot can always see, right? And I can constrain the problem so the robot always sees that stick, and that stick gives me information about orientation, like it's a whatever, some imaginary stick that gives me all those things, right? Then I wouldn't use a LiDAR, right? Because I can just use the stick to get the service of knowing where the robot is. And there's multiple technologies there. So, sorry, coming back to the breakdown of the robot. I've got a bucket, and the bucket needs to have things put into it, and the bucket needs to go from one place to another place, right? And I want the bucket to do that without me touching it. So the bucket needs to know where it is, right? So that's called localization. The bucket needs to not run into things. So that's obstacle avoidance. The bucket needs to come up with a series of poses that it should travel through, right? That's navigation. So if we were just to like stop there, right, and talk about this like one technology thing, right, we need to talk about, let's say, localization first. We're talking about localization. There's multiple technologies that can help with that. GPS is obviously the first one everybody thinks of who is in a roboticist, and even roboticists. It's important to know, and anybody who has been to the competition in California called RoboGames and participated in the Magellan competition, they would know that GPS is only accurate to about 10 meters. So like there's this like circle that's like 10 meters wide, radius, diameter, not sure, that you can know where the robot is. But when you're trying to not hit a tree, that doesn't help, right? So GPS is only accurate to like a certain amount, right? So you have to use other technologies. RTK GPS is another one that is really well used, right? If you're in a farm, right? A tractor might use RTK GPS. So they'll add another GPS receiver and a wireless communication so the robot can talk to that and get centimeter accuracy, right? You don't need a LiDAR there. In fact, the problem in that scenario with a LiDAR is that the field is usually so big and wide, a LiDAR doesn't usually have enough range to see anything, right? So in that scenario, you might have to be forced to use RTK GPS and some sort of camera modality for helping localization. Visual SLAM is not something that is as popular or well understood, right? As LiDAR-based SLAM. 2D LiDAR-based SLAM is particularly well suited, but obviously autonomous cars use 3D LiDAR, right? Why would you use 3D LiDAR? Because you get more range measurements to like line up with, right? To like check yourself. Whereas like the 2D picture, you can get a lot of false positives depending on your environment. Localization is completely environment dependent. So you need to choose a mature enough technology to do localization, to get the robot to know where it is, right? So a 2D LiDAR might do that for you. If you were to go with a 2D LiDAR, the requirements for a localization LiDAR versus an obstacle avoidance LiDAR would be different. So it's typically really important for a localization LiDAR to see very far away so that you can have a good enough, wide enough picture to get lots of measurements to reference off of. Because essentially, when you boil it down, LiDAR-based localization is doing something called scan matching. You can think of it as like I've printed out a a floor plan for a room, and then I move somewhere else, I print out a floor plan of a room, and I'm trying to line them up, right? So you need enough points to line up so you can see that those things match. But that's really different than an obstacle avoidance based sensor. Usually you want something relatively close, and you don't care for something relatively close that has a lot of points densely, but you don't care so much about what's 30 meters away from you. A really great example of this for me is there's a LiDAR called the Livox. The Livox is a relatively inexpensive LiDAR for the number of points it gives you, but it does this single beam scanning pattern, right? And if you're doing obstacle avoidance, if you're doing obstacle avoidance and you're moving, relatively close to things and not too fast, that density is enough to kind of like feel your way through the world, and you're just trying not to run into things. This is another thing from manipulation people, from arm people to navigation people. Arm people usually are concerned with touching things, and navigation people usually don't want to touch anything, right? They want to try as hard as they can not touch things. So this sensor is probably pretty good for the obstacle avoidance. It's 3D, right? That scratches a lot of itches for mobile based obstacle avoidance. But because it's got this sweeping pattern in time, the LiDAR scans further away start to smear. And so a lot of the localization algorithms you might have used before, which tend to assume that this is a snapshot in time, are not correct, right? And so in my experience, the localization companies that worked with this sensor, they need to time register every distance measurement and take that into account in their LiDAR scans. So if you were able to separate that out for your budget to a 2D LiDAR and a 3D depth camera, that could be really good. In my experience, you need to have as many depth cameras as you can. In the ideal world, the robot could see 360 degrees for obstacle avoidance, because you as a human being take for granted the idea that I can't quite see anything anymore, but I remember that it's here and I can behave accordingly. And robots have trouble with that sometimes. So if you could just see it, you wouldn't have that much of a problem. So to take that all back for a second, right? You shouldn't start with the assumption that I'm going to use a LiDAR and I'm going to use a depth camera, right? You should start with, I need the service of knowing where the robot is, and I need the service of not running into things, and try to figure out which technologies help match you up to that. And it's very, very problem dependent. It's not going to be the same for all problems, even though you might be familiar with a lot of robots that have a LiDAR and a depth camera, and that just works. Obviously, cost is a big constraint there. So now that you've done that, right, now, obviously, I'm going to say that you should use Nav2 because it's excellent software. You need some sort of technology that allows you to use those sensors to plan and obstacle avoid and localize control, right? So you need to be able to choose how many wheels or treads or legs that your robot has and be able to get the platform to move. One of the things I always think about, for example, the go-to robot, right? The Unitree robot, is that quadruped has become remarkably cheap. I'm sure that if you're going to do it at a professional scale, that you can negotiate a better price than their development license. But that robot is remarkably cheap for a hobbyist, for sure, to the point that I think that if it fits your use case, for example, last mile development, like I need to deliver the Chipotle, right, from the restaurant to somewhere in Mountain View, I would argue that it is cheaper and more time cost effective to just buy a fleet of those and skip mobile-based development with wheels, because there's enough challenging environments in that urban area that you've got to do like that 6-wheeled NASA configuration that the starships had to do. So you need to decide on mobile-based technology, right? You need to decide on how to control that technology, and that's just to start getting the robot to do something. Now, let's say we had like, what's the name of the Boston Dynamics dog?
I don't know. I don't remember
Um,
either.
Spot,
Spot.
right? Spot has had maybe some challenges finding a good product market fit, right? Even though it can tick a lot of those boxes. One of the most compelling ones I guess I've seen is walking around a industrial area and taking pictures of dials. Okay. So let's say, that kind of goes back to the whole like run a robot through a warehouse and take pictures of things, right? Um, Now you need to deliver all of that information to the customer, right? So does somebody just SSH into the robot and download pictures? No, of course not, right? You need to think about your strategy of offloading that data. How much of the processing is going to happen on the robot? At Bossa Nova, we went back and forth on this, right? How much the robot was going to do analysis, right? Essentially, you've paid for lots of computers to be deployed to the fleet, right? Are you also going to pay for cloud services? Which you may say yes, you may say no, right? Those robots spend a lot of time idle, but also you have to develop an infrastructure for distributed computing, right? As opposed to like just uploading things to the cloud and maybe trying to like crunch through in one processor, right? And then you've got to present that data, right? So there's a whole analysis piece that I'm just skipping, right? But you can imagine the problem of ingesting images, doing machine learning to pick out things, or classical algorithms to segment pieces of those things and identify what's in the image and turn that into data. And then the data needs to be analyzed and turned into information that can be presented to the user, right? In the Bossa Nova use case, right, we would take the images and we wanted to take the barcodes and like scan the barcodes and figure out what product was supposed to be there on the shelf. And then the picture was supposed to help determine whether or not there was an object there. And if there was an object there, is it the right object? And so all those things need to be crunched together in the database, and then you need to see it, right? So it's several companies all packed together, and the robot is just one piece of it.
Okay, interesting. That's a lot to cover. Next, let's say we decided the robot and we are moving towards the software. And the thing that I want to focus more on is the software that involves hardware and the software, meaning it's not just the simulation. So I'll again bring up the easy project of a robot that performed 2D navigation, 2D slam, and all of these in the warehouse to keep things simple. So once after deciding it, so coming to the point of writing the software, you suggested nav2 usage for navigation. We would be using other ROS2 stacks for mapping purposes. Once that is done, the basic process is done. We need to engineer it. There comes the part of testing and engineering the already available stacks, writing plugins. How do you look at these things? How do you write the tests of all of these things?
Yeah, so you asked about software architecture in robotics. So as somebody who would advocate for doing, if they were to do their own startup and you wanted Grizz's opinion on that, I think that you should use ROS. I come from a background where people used ROS and then they tried to get rid of ROS. I'm not sure if that's appropriate anymore. I think maybe it was more appropriate before. But conversely, I would say that there shouldn't be any ROS in your robotics code. And this is like a weird thing to say as somebody who would like advocate for ROS. And actually, one of the talks I had proposed in one of these conferences was how to get ROS out of your robot, right? And the reason that I say it like that is just to be cheeky and like to get people's attention. Really, the challenge is, as someone who's a software engineer, that there's two ways that software can deliver the result. Okay, this is like going deep into software engineering theory now, right? There's maybe the concept of something called a pure function, right? Where something goes into a function and then it comes out the return value of the function, right? And so we'll call those things pure. The opposite of pure is side effect, right? So when you print something to the screen, instead of having it come out through the return value, that's a side effect because you can't see what happened just through the return value. So for example, if you're going to write a test for something that printed to the screen, right, then you'd have to have another program launched that captures the output from the screen, right? Save that to a file, perhaps have something open that file and then process the text that's in there and then somehow communicate back to the original test function, right? That becomes a real challenge when you're writing software at scale. So ROS, right, I think is a very important technology for doing component-based software design where you have multiple applications that are logically independent of each other but need to communicate with each other to form a system. Doing the publishing and subscribing in ROS is a side effect, right? And what tends to happen with a lot of software engineers who write ROS, and in some ways I blame the ROS documentation for this because they prescribe this way of writing the code. And, Will Woodall and Tully can challenge me after this, but I think they would agree, right? That that means that ROS ends up getting baked into your code. And look, if you're using MQTT or I forget what the Rust libraries that do async communication are. If you're using any of these other technologies, the advice would be the same, right? I don't mean to pick on ROS here, but as someone who advocates for ROS, I'm going to pick on ROS because ROS is the technology I'm going to use for the service, right? So you need to separate your logical code from your side effect bearing code because ultimately, your side effects, that's the whole reason you're writing code, right? If you were writing the code to compute some numbers, but you never printed the screen, then why did you do it? The only thing is it could be a space heater, right? It helps warm your house. You never get anything out of it, right? But in software engineering, there are these techniques you can use to kind of push all your side effect bearing code to the edges of your code so that the bulk of your code has no side effects. And so this technique is called dependency injection. Functional programming, right, couples with dependency injection, where you might use a lot of functional programming techniques to write a lot of your software, and then to get to the side effect bearing code, use dependency injection. My colleague Bilal Gill gave a great talk at CPPCon 2023, hour long, about ROS, functional programming, and dependency injection. I advise everybody to watch it if they want to know details in context. Which, by the way, CPPCon has a robotics track for the last 2 years now. You should apply. But so while you're writing your own software, let's say you're using the nav stack and you don't have to touch the internals of the nav stack, right? Maybe you have to write some plugins for the nav stack or some controllers. You need to be thinking about a whole bunch of software design and engineering principles, but I would lean on those two first, right? As things that'll help you get out of a lot of trouble, because really, right, this is a endurance sport, right? You need to write maintainable software, not just software that works right now. Though having the mindset of being able to throw away your code helps you say, I'm going to write the code I need to write today, see that the idea works or is even feasible, and then if it's worth keeping, turn it into more maintainable code. But that takes discipline. You need to be disciplined in order to know that you should throw it away. And if you get too attached to code, you tend to not throw it away. Because in my opinion, the thing that saves the company, right, or saves the project, saves the product is something called a layered testing approach, right? So there's some big names for tests that you might call a unit test, an integration test, in robotics, a simulation test, and an on-robot test before you ever get to something called manual QA, right? Where a human being takes the robot, touches it, and tells it to do something, right? I've been at companies before where there were only manual QA. And frankly, our software release cycle only was ever finished testing in an entire 1 whole year, right? Before you could finish the testing suite because everything was so arduous to do. In those sorts of scenarios, to put it bluntly, in order to test that 1 + 1 = 2, you have to take the robot out into the field and drive it across the strawberry patch or whatnot, right? And it's a big challenge. So unit tests, right, should serve the purpose of checking to see whether or not the logic of everything that you're writing works. It should all be, I'm just going to lump everything that doesn't involve side effect bearing code into unit tests, right? I would say integration tests are those things where you have to have a system. You need to have Ross talking to another node, right? Or outside of Ross, a friend of mine worked for a drone company, right? And maybe the drone has to read some files, and get some waypoints and process those, right? That starts to be maybe just reading the file is like not as much, but it has to talk to another system, right? Maybe that starts to be integration tests. And then simulation tests, to my mind, are those things where you need to provide a lot more context. They're very similar to integration tests, but the feeling of integration tests are more like systems are just talking to each other, whereas like a simulation, you need something to pretend to be the environment. And as we were talking about before, sometimes those may be physics-based simulations, right? Sometimes if you're making a walking robot, for example, right? You really care about how you hit the floor and your controller responding to something like that, right? And so for the controller tests for that, you really care about the simulation. But if you just have that mobile base example and you're just going around the warehouse, really, if you can get away with a non-physics based simulation that gives you LiDAR returns and helps position the robot, you should. It's going to run faster. There's a lot of context where you're doing a test with an arm, right? And you just need to know that the kinematics got the end effector close to the target, right? So I would lump everything that's simulation test into needing to provide some sort of exterior context or environment. And then there's the on robot tests. Now, the easiest thing to do is for you to like start up your robot and do something. But if you can, and I always call this like this whole layered testing with the on robot, automated on robot test, my platonic ideal, right, of what a robot stack should look like, is that you should have a system to automatically launch the robot and run some limited scenarios, like the real world robot in a physical place, right? So like if this was an arm, you might just have it pick something every night, just make sure that that whole stack works. But honestly, there's something called a wiggle test when it comes to robot testing. It's just like, can the software be loaded onto the robot? Can the robot start? In the case of an arm, why it's called a wiggle test, it's just like you might have the joints move like a degree, right? Just like, could I command them? Could the controllers do something and they just barely move, right? And it doesn't do anything else. And they just kind of like make sure the whole state of the software is working and well integrated. A mobile base, you might just have it like move forward half a meter and then dock again. But you've had to exercise a lot of systems just to get it to undock, command, drive, come back, dock. That's the whole pipeline that just happened, even though the robot didn't do very much. At Nito, I used to have a testing suite where they would run missions every night and then come back and dock, and then we would share the data with the developers for each branch. So to me, there's some set of automated tests that you can do, and then the manual QA happens where a human has to look at it. But manual QA is always going to be the most expensive. And if we wanted to talk about scale, I would say that in a functioning product, you've got thousands or tens of thousands of unit tests. You've got hundreds of integration tests. You've got tens of simulation tests. You've got tens of automated tests, automated on robot tests, and you've got tens of manual QA tests. Maybe a little bit more for the manual QA, but the orders of magnitude, right, funnel down to something, very narrow. I had a friend who worked at this great drone company, and they actually had shipping containers filled with drones that were fixed in their shipping containers, and they would run simulated missions every night. So all the hardware was actually actuating, the motors were running, even though they removed the propellers. They had, the encoders running, the processor itself was computing all those things for the simulated mission. They call this hardware in the loop testing, right? That's great, right? If you can do some sort of that, because you can flush out so many bugs and help write more maintainable software. And everything else about the architecture can be improved if you can make a maintainable pipeline that helps you write software. I actually have no personal interest in code quality other than it allows me to continue to write software. That was the only reason I ever started talking to people about it, about why you should do one thing or another. And it also takes some discipline to remember why you care about things. People definitely get in rabbit holes and what's called bike shedding. There's this expression in software engineering where if someone's trying to design a nuclear missile silo, right? Everybody is like, oh, well, I don't know. The experts should deal with that. I don't know what to say. But then they have this project where they build a bike shed, a little roof for bicycles. And then suddenly everybody has an opinion and they all argue about the color and like, which kind of nails you should use and whatnot, right? And there are things that matter much less, right? And so you always need to remember the goal. You need to invest in quality so that you can keep writing software, making robots work. My friend and colleague Davide Facante, he has a great Twitter account. He'll tell you about this all day, right? That like he's very invested in quality, but the robot needs to work first.
Definitely.
That was a
So
lot. Sorry.
no, this is important because when we are working, we definitely, everyone I think starts with making the robot work, but they get stick to it and they start to add features into just that approach of making features work and then move toward making this product just work, not an approach or structured approach that will bring the quality to the product. Coming to the point of when you were working at Bossa Robotics, you led the refactoring of the navigation stack for them. Can you share what prompted this refactoring and what was some of the technical and non-technical things that you experienced?
Sure. So I'll mention that I was one of many people who led the refactor. When you're a startup, right, as we just mentioned, you need to make sure things just work, right? And a lot of this has to do with you don't have infinite time and you definitely don't have infinite money, right? And you need to show value to the customer and to the investor. So this caused that company to do some things that were difficult to maintain. They had some business logic that was mixed in with the navigation code. And the main issue was that those separations of concerns were being violated. Those things weren't well maintained. And the only test that didn't involve the manual QA was a particular engineer looking at the simulator and saying, yep, that works, right? So it was very hard for anyone to understand what was happening. Many of my colleagues were able to remove parts of the business logic that dealt with actuating the lights and turning on the cameras, right, for their own separations of concerns. This is one of the great things about componentized design, right? When I was at Nito Robotics, right, there weren't separate executables running, so everything was baked in. Now, honestly, Nito had better separation of concerns than Bossa Nova did in those early days, right? But still, everything was like working together. And in Bossa Nova, they had used ROS, they weren't taking advantage of the fact that things could be separate and actuated through services, which have their own challenges. We had a lot of issues with the middleware not delivering messages sometimes and having to work through those. I'm sure anyone who's worked on ROS 2 will have the same comments, just in a different way. So the code had become what's called monolithic. It had not become what my colleague and friend Mike Ferguson had called ossified, because we had complete control to change it, but it had become monolithic. And so it needed to increase separation concerns so that more people could work on the software, frankly, independently of each other without stepping on each other. And it needed a different way to test it, right? So that the pieces could be automatically verified or verified by more than one person. Frankly, we took that same test that one guy did and figured out what he was looking at. And even just the act of writing it down, right? Even if you still had to have somebody look at it, itself was helpful. Now, we were able to automate a lot of those tests, and then they kept breaking. Even when the test broke, then you could refer back to what's the test supposed to be doing, right? So really the refactor of the navigation stack there was kind of just about survival, right? You needed to keep writing software, and it got harder and harder to take the next step, right? And that's really what all these quality practices are about, right? I need to take the next step, and the software itself is stopping me. To go back to competitions, for example, we worked on the RoboGames Magellan competition, and a number of us were working on the hardware integration, and our one teammate was working on most of the software stack that he wrote himself, and he used all these practices. We were also good software engineers, but once we're like, okay, we're done with the hardware integration, let's help you with the software. Nobody could understand what the software was doing, right? It was so tightly integrated and bespoke to this one engineer, right, that we couldn't help him, even though now we had time. And he had to change everything himself manually. And there was too many things for him to even change. So similar concept to what was happening in Bossa Nova, right? And this is not unique to Bossa Nova. Many software companies, right? They'll just pile a lot of software into this monolith that is difficult to understand if you're not the person who wrote all of it. And honestly, the person who
Hey,
wrote all of it has a lot of hard times understanding it because you're
mm,
not the same person you are today as you are tomorrow. And especially next week, 6 months later, after you've had so many meetings and you've pivoted your whole product to something else.
yes, definitely. Coming to the part of learning, the ROSCON CPP that you mentioned earlier, robotics chapter. That's amazing. I just recently came across as you provided some intro to it, and after going through it, I understood one very important thing, that when you first start, you try to make things work. Then you get to, after graduating, you get to the point of creating software. And after spending some time, you get back to the algorithms that you have studied and you try to go deeper inside of it. Why is that the case?
So, people who are getting into robotics, that robotics is probably about when you're in industry, right? Professionally doing a product, doing a software as a service. The algorithm part is probably about 10%, 5% of the whole software stack. And the majority is just writing good software. But somebody who is, for example, a web developer, right? They don't have the appropriate context for writing robotic software and what the robotic software is going to need and why, right? And so when you're at academia, right, you know, unfortunately or fortunately, it's hard. I go back and forth on like what's appropriate here. You're focused more on the abstract concept of how robots should do robot math, right? Because ultimately everything comes down to math in a robot, right? I mean, it's a computer, so everything is going to
Definitely.
come down to math, and you have to understand robot math, transforms, kinematics, controls, probabilistic sampling for planning, right? All this robot math. And that gives you the context for what you're trying to do with robots, right? But they're not going to teach you to be a good software engineer. They might teach you how to become a programmer. They should teach you to become a programmer. So you have basic competency there. You need to take it, from yourself to become better at that before you go into industry. But that gives you the context for what needs to happen. And then you go into industry, right? You actually need to make it work. And you're going to spend a lot of time making it work, especially, hopefully, most of algorithms have been written and are reusable. Hopefully. This isn't always the case. Navstack, Move It, these are great examples of places where you can find lots of reusable algorithms and systems, right? But again, those are technologies, they're not products, right? They're not the whole project where you need to get the robot to do something. And so you're going to spend a lot of your time connecting pieces, right? And making sure the way you connected them is right. The way you specified the parameters, the way that you ingested the camera images and delivered the results to the right places. So you spend all this time figuring out how to do that, right? And becoming good at it. And so then over time, and I think Sebastian Castro, who you interviewed previously, he said this as well. Over time, you know, that becomes more second nature, right? And maybe you're interested in that, and that's where you stay. But if you're somebody who was interested in algorithms, now maybe you kind of have the breathing room to get back to where you started, where it's like, well, now that I've got the skill of being able to write maintainable software, I can get back to writing algorithms so that I can create maintainable software or new algorithms, right? Now I've learned all this maintainability skill and I can see that, this library isn't maintainable or those function parameters cause me to make these design choices, right? And, I can write it better. And you definitely you definitely delude yourself into thinking you can do it better than the other guy. And then you try it and it's much worse. But again, going back to all the way in the beginning, you only get better at writing software by writing software, right? And you need to be able to throw your projects away, but you gained something in that process. So you need to give it a shot as a senior engineer and try to write these libraries and let them be terrible, right? and then throw them away when they're terrible, and maybe you try again, and you maybe you get better at it, maybe a few of you get good at it, and you're trying to like deploy this software. Again, going back to my friend and colleague Davide Ficante, right? uh you don't become somebody who writes a whole new like popular ROS package a year or every year and a half or so on by just, you know, thinking about writing software. Davide writes a lot of software and then gets an idea that he's going to try to solve this problem for voxelization and making an open source library, right? Or data collection in a performant way, right? And both of those, he has a story and a journey before like he released the library, right? And so from the outside it looks like he's just producing libraries, but he's written lots of software along the way and thrown away lots of software, right? And so it's kind of like you need the context, you need the skill, and now you can start to actually produce something maybe you're a little more proud of. And I think that's where, as you become more senior, you either go towards management, architecture, or maybe deeper algorithmic development or research, right? As Sebastian Castro would tell you, right? Going into the research field where it's like all new things, but you've got a little bit more experience to reach, to not hit certain pitfalls, and then maybe you're back here guiding the junior engineers right into the new algorithmic development, and then the cycle right continues.
Perfect. Let's finish with this important question, and that is related to communities. I found out that you have also started a community in your area, and communities have helped you a lot in getting to the roles that you have been in the past. So, what do you think about robotics communities in an area and how they affect?
So I would say the robotics community is very small. Not even just the ROS community. The ROS community is smaller yet still, right? But the robotics community as a whole is relatively small, which means you get to know a lot of people, right? There's this old thing about 7 degrees of separation. I'm very less than that towards a lot of people in the robotics community. 1 or 2 often, maybe 3. And so you need to get your name out there. Software engineering is a team sport, right? There's very few people that I know who are completely siloed, right? In fact, I probably wouldn't know them if they're completely siloed. I'm forgetting the name right now, but in C++, there's a guy who writes the Circle compiler, right? And he writes, I think, most of that himself, if not all of it himself, right? There's very few people who write these big projects and they do it completely alone. So programming is a team sport, but robotics is not so abstract or general. IT. So I used to be in network security, right? Briefly doing IT work, right? And I felt comfortable, applying to Indeed or some other job search website, Monster, back in the day, and like having a reasonable expectation that that was a viable pathway to getting an interview, finding a career. And in my experience, that wasn't the case. Throughout my entire career, for me to find a job, it always involved me having a previous contact that just helped me get the interview. Once you get the interview, now it's all your responsibility, right? You need to bring the skills and the energy and being able to clearly communicate with people that you could provide value, right? That's all up to you. But it just gets to be challenging to just get the interview. And in my career, I usually, when I was in university, right, once I graduated, I applied to a bunch of companies and I heard back from none of them. Not a single one. No responses at all. The only way I got a job was that I used to go to this competition in Connecticut called the Trinity Home Firefighting Robot Competition. Some ridiculously long name. I'm mixing some of them up. Where you went and you would build a small robot that would search a maze and find a flame and extinguish the flame, right? It was like FIRST, but with more autonomy, right? In FIRST, when I say it's like FIRST in the sense that, this is a problem that has a context and there's multidisciplinary. But it was always completely autonomous. Micromouse is another example of such a competition, right? And then in the Bay Area, they have a version of Trinity at RoboGames. The point is that I would participate and I would talk to people, right? And I would talk to people who were from different parts of the country, the world, right? Their experiences. And one of those people happened to be doing a startup, right? And I always tell junior engineers when they're trying to get a job, it's more important that you get the first job than for it to be your ideal first job, right? You need to get into the community and into the industry, and then you can work towards, branching, going towards the thing that you want, right? Because it's a career, it's not a job. So after that first job, right? I got my next job because I attended Homebrew Robotics Club in the Bay Area. So there was Homebrew Computer Club, which where like Apple and Microsoft, got their showing. And then after computers became ubiquitous, the Homebrew Robotics Club took its place. And a number of robot startups in the Bay Area, Fetch notably, or Unbounded, they presented there. And so I got my job at Nito by connecting with people there. So you need to connect with people over and over again so that you can be available for opportunities or know when opportunities are coming. And somebody can refer you and say like, oh, well, I know they are at least basically competent and they're worth speaking to, right? And that usually goes a long way towards getting the interview. So my contribution to that, aside from I'm the track chair for the robotics track at CPPCon. The reason that I wanted to start the robotics track at CPPCon is that C++ is very prevalent in the robotics community. And while we might prefer other programming languages in the future, Rust notably, maybe someone wants to write their algorithms in Julia, for just like the math part, right? There's going to be a lot of C++. And C++ has a lot of foot guns. It has a lot of ways of getting in trouble. And people come up with lots of exceptions for how to use C++. And at CPPCon, for the robotics track, I would like to show people that there are lots of examples of people writing good quality, maintainable C++ in the same context as you, right? But so aside from, plugging my conference track, the other thing is that in the Bay Area, there was a company called Willow Garage, many people will know, right, that started Ross, and the employees there used to play board games. And once Willow Garage dissolved and people were going to their own startups, they wanted to maintain that connection with each other. And so this became going to each other's startup and playing board games there, which became people inviting their friends and became a whole very low key but frequent networking opportunity where you go to the startup and you see what people are doing and maybe they're hiring and you know who's looking for a job, or you're always just keeping your ear to the ground there. And that helped me when I was in the Bay Area connect with people and then get the next job, right? So I recently moved to Boston, and talking to my community of people here in Boston, found out that there was no such networking opportunity. So we just started a chapter of board games for robotics people here in Boston, which we try to go to each other's startups. We've been to, the AI Institute. We've been to Gaia AI. We've been to, there's a list on the website that I have, not remembering it off the top of my head, where we go to those startups and we try to see what they're doing, play board games with each other, socialize, see who's looking. And so I think that, as we build that community here, right, Mass Robotics is involved, that will help other people find, new places in their career path. And that's my hope anyway. And I think that's very important. I think that's how you build community. I think that's how you build a career.
Definitely. Thank you for all of this deep information and experience sharing. It was really nice to have you here, Griswold. And
thanks for having me, Lukman. Hope to join your podcast again in the future.
Definitely. Take care.
All right. Bye now.